Every time you instantiate an object in Java, you pay an invisible tax. If you define a class with just a single 64-bit long primitive, you'd expect it to occupy exactly 8 bytes of memory. But on a standard 64-bit JVM, that exact same object instantly inflates to consume 24 bytes on the heap. This overhead hits hardest in massive in-memory caches, high-frequency trading pipelines, or microservices managing millions of objects. At this scale, a significant portion of your infrastructure budget is consumed by JVM metadata rather than your actual application data. This bloat consists of JVM metadata that remains completely hidden from your source code. For decades, this overhead was simply accepted as the fixed cost of doing business with modern managed runtimes. But right now, structural shifts and modern execution engines are rewriting exactly how the JVM manages bits on the heap. Mastering this hidden layout is how you break past hardware cost constraints in high-throughput cloud architectures. To see where this hidden cost comes from, we have to look past our variables and use the Java Object Layout tool, or JOL. This output shows a standard JOL trace. When run on our simple class, the total instance size is confirmed right here, 24 bytes. The trace breaks down exactly where those bytes go, isolating the space reserved exclusively for the JVM's metadata injection. That initial 16-byte metadata block acts as a mandatory toll booth attached to every single instantiated object, dictating the baseline performance limits of your application before it even executes logic. This diagram illustrates standard Java object memory layout. Looking at the left side, without compact headers, we see the legacy object header. It's a fixed 128-bit structure, split evenly into two distinct components. The first component is the 8-byte mark word. This acts as the JVM's Swiss Army knife. It changes its bit-level meaning dynamically to track the object's locking states, generational garbage collection age, and identity hash code. Right below it is the second component, the 8-byte class word. This is a crucial native pointer, linking the object instance directly to its metadata representation in the metaspace, allowing the execution engine to know what methods are available at runtime. And at the bottom of the structure, we have the final space waster, alignment padding. The JVM requires objects align on strict 8-byte word boundaries for optimal CPU cache line alignment. If you change your payload from an 8-byte long to a 4-byte integer, the math doesn't line up. So the JVM injects 4 bytes of empty air just to hit that strict 8-byte boundary. Combine that rigid 16-byte header with forced 8-byte boundaries, and your microscopic application data inevitably balloons into massively inefficient heap allocations. Memory footprint is the primary driver of cloud infrastructure costs, and Project Lilliput targets this exact inefficiency. Its objective is mechanically brutal. Compress the legacy 128-bit header down to just 64 bits. Achieving that level of compression requires completely eliminating the 64-bit class word native pointer. Instead of a full 64-bit address, Lilliput introduces a compressed class ID. This ID operates as an encoded index, mapping to a class table, removing the need for a direct memory address into the metaspace. Lilliput packs this class ID directly into the underutilized bits of the existing mark word. Because the ID is safely hidden inside the mark word, the discrete class word structure is entirely deleted from the object layout. Having the header allows our 8-byte payload to shift up, tightly packing the overall memory block. By merging these critical data structures, the entire object naturally fits within a neat 16-byte boundary, structurally bypassing the need for alignment padding entirely. This bash terminal text shows the exact flag needed to trigger this parser shift in a production environment, unlocking compact object headers. Looking at the layout diagram on the right, the result is immediate. The class word is gone, and the total allocation drops from 24 bytes down to a 16-byte footprint. When applied to massive microservice deployments operating in the cloud, the math becomes highly favorable. Flipping this single JVM configuration flag yields a 10 to 20% decrease in overall heap usage, which directly lowers GC pause times and cuts your infrastructure invoices, all without changing a single line of application code. But singular object overhead is only half the equation. The secondary memory problem in Java is the massive performance cost of scattered pointer indirection. When developers write arrays, they generally conceptualize them as densely packed, contiguous blocks of sequential data. But an array of objects in Java is actually a collection of 64-bit native references. The actual instance data isn't sequentially loaded in the array. It is scattered arbitrarily across the entire heap space. This causes severe hardware friction when a CPU attempts to iterate through your array. Chasing these random pointers across memory guarantees continuous L1 and L2 cache line misses. Instead of processing data, the CPU is forced to sit idle, waiting for main memory fetches at every turn. This is a stark contrast to C-structs, which keep data perfectly adjacent for optimal CPU cache utilization. Even the most heavily optimized algorithm will bottleneck at the bare metal level if the processor spends the majority of its execution cycles blindly chasing fragmented pointers. This is exactly what Project Valhalla aims to solve. It introduces value classes as the definitive solution to array fragmentation. A value class is an object that explicitly declares to the JVM that it lacks an independent identity. By declaring this, you trigger a mechanical shift. Because there is no identity or locking state to track, the entire object header becomes completely obsolete. The JVM reacts by fully stripping the header whenever it embeds these objects inside an array. Valhalla deletes the pointers entirely and flattens the raw fields directly into a contiguous memory stream. This flat memory layout behaves identically to a C-struct, providing unbroken sequential chunks for the CPU to process at peak efficiency. Now that we have the memory layout optimized, our next bottleneck is concurrency. In the next episode, we will look at how the virtual thread machinery executes concurrent operations on top of this flattened heap. By combining header compression with flattened arrays, the JVM achieves the contiguous layout typically reserved for low-level languages, ensuring object iteration is limited only by CPU cache speed.